Welcome to this presentation on CFAR radar detection, presented by Professor Gottapu Sasibhushana. As shown in the figure, radar must detect the target even when the received echo is mixed with noise and clutter. The receiver has three important objectives: maximize the output SNR, obtain good range resolution, and make reliable target decisions using CFAR. The CFAR process is shown in three simple steps. First, the surrounding reference cells are used to estimate the local noise or clutter level. Next, an adaptive threshold is calculated as T equals alpha times the estimated noise power. Finally, the power in the cell under test, or cut, is compared with this threshold. If the cut power is greater than the threshold, a target is detected. Otherwise, no target is declared. So, the overall idea is simple. Matched filtering improves SNR, large bandwidth improves range resolution, and CFAR provides reliable adaptive detection in changing noise and clutter conditions. Now we come to the basic conflict in radar detection. As shown on the left, if the detection threshold is set U low, even noise or clutter can cross the threshold. This gives many false alarms. If the threshold is set U high, false alarms are reduced, but weak targets may be missed. Only strong targets may be detected. The lower graph shows this clearly. The blue low threshold gives more false alarms, while the red high threshold can miss weaker targets. A strong target crosses the high threshold and is detected. The processing chain at the top shows the received echo passing through the matched filter, range cells, CFAR detector, and decision logic. So, a fixed threshold is not suitable when noise and clutter change. CFAR solves this by adapting the threshold to the local noise and clutter level, giving a better balance between sensitivity and reliability. Now we see how the radar receiver improves signal quality and range resolution. On the left, the noisy received echo is applied to a matched filter. Its impulse response is shown as H of T equals K times S star of T minus T. The matched filter produces a sharp output peak and gives the maximum output SNR. The relation shown is S by N, maximum, equals to E by N0. On the right, range resolution is explained in two ways. For a simple pulse, delta R equals C tau by 2. So, a smaller pulse width, tau, gives better range resolution. For pulse compression radar, delta R is approximately C by 2B. Therefore, a larger bandwidth B gives a smaller delta R and better separation of two closely spaced targets. So the key idea is, matched filtering maximizes SNR, while small pulse width or large bandwidth improves range resolution. CFAR is then used in the next stage for adaptive detection. Now we come to the three basic steps of the CFAR algorithm. At the center is the cell under test, or cut. On both sides of the cut, we have guard cells, followed by reference or training cells. In the first step, the reference cells are used to estimate the local noise or clutter power. The average is calculated as P hat n equals 1 by n into the summation of xi. The guard cells are not used in this averaging. They protect the cut from energy leakage of the target signal. In the second step, the adaptive threshold is calculated as T equals alpha times P hat n. Here, alpha is the scaling factor selected according to the required false alarm probability. For CFAR, the relation for alpha is shown at the bottom. In the third step, the cut power is compared with the threshold. If xcut is greater than T, a target is detected. If xcut is less than or equal to T, no target is declared. So, CFAR continuously estimates the local background and changes the threshold accordingly. This keeps the false alarm rate nearly constant even when noise or clutter changes. Now let us apply the CFAR steps to a simple numerical example. We use 8 reference cells with values 2, 3, 2, 3, 2, 4, 3, and 5. The two guard cells, G1 and G2, are not included in the noise estimate. The average reference cell power is 24 divided by 8, so the estimated noise power is 3. With the scaling factor alpha equal to 4, the CFAR threshold becomes 4 times 3, which is 12. Now consider the cell under test. Its value is 18. As shown by the graph, the cut peak at 18 is above the red CFAR threshold line at 12. Therefore, since 18 is greater than 12, the radar declares target detected. This example shows how CFAR converts the local noise estimate into an adaptive threshold and then makes the final detection decision. This slide summarizes the complete CFAR radar detection chain. First, the radar receives the echo signal. Next, the signal passes through the matched filter. The matched filter maximizes the output signal-to-noise ratio. Its response is represented by h of t equals k times s star of t minus t. The maximum SNR is shown as S by N maximum equals 2E by N0. The filtered signal is then divided into range cells or range bins. The range resolution is approximately delta R equals C by 2B. So, larger bandwidth gives better range resolution. Next comes the CFAR detector. Reference cells are used to estimate the local noise power, while guard cells protect the cell under test. The estimated noise power is represented by p hat n, and the adaptive threshold is T equals alpha times p hat n. Finally, the cut is compared with the threshold. If X cut is greater than T, the target is detected. If X cut is less than or equal to T, no target is declared. So, in one line, matched filtering maximizes SNR, bandwidth controls range resolution, and CFAR provides adaptive thresholding with a controlled false alarm rate.